Hi everyone, so we're going to be talking about something called the Binomial Theorem, and this is just a little intro to that. So take a second just now and pause the video and work on these problems just for a second, see how far you can get. You're probably not going to get very far with these last few, but try to just expand, simplify, expand these out as much as you can. Alright, so hopefully you've tried those. Let's go over some of this. So, what is anything to the 0 power? That is always a 1. If it's 5 to the 0 power, or if it's anything to the 0 power, it's always just a 1. So we know how to do that one. Anything to the first power is just itself, so that's just x plus 2. Be careful on number 3. A lot of people on this one are tempted to do x squared and 2 squared, but that's not all that there is to this one. And if we write it out, you'll see. So if I want to do x plus 2 squared, that means I want x plus 2 times. X plus 2 times x plus 2, which really means I need to distribute the x and distribute the 2. So I'll get x times x, which is x squared. X times 2 is 2x, 2 times x is another 2x, and 2 times 2 is 4. So there's a lot more here than we originally thought. 2x plus 2x can combine, and we'll get x squared plus 4x plus 4. All right, on the next one. Again, you can't just cube both of those. The plus sign makes it complicated in there. Since there's multiple terms, you can't just cube them. So, like we did here, we're going to need to do x plus 2 times x plus 2 times x plus 2, because there's 3 of them. So you're going to need to distribute this, and then whatever you get, distribute to another x plus 2. I actually have some of that. I did this right up here. We already know that x plus 2 times x plus 2 is this. So I'm going to substitute this in right here. So I'm just replacing x plus 2 times x plus 2 with what we got, and then we need to do times another x plus 2. That's going to be a lot of distributing. So we'll do this times this times 2, this times x, this times 2, this times x, this times 2. I'm going to go ahead and stop there. As you can see, this is getting pretty messy. We could do it, it's just going to take a really long time. Imagine how long it would take if you were going to do this 9 times, or even 4 or 5 times. It's just going to take a while. So we have something called the Binomial Theorem, and it's a way of expanding binomials, so something with 2 terms, to a really high power. And it's kind of like a formula that you can use to expand binomials. And before we get there, there's a tool that we're going to use, and I want to introduce that tool to you in this video. So it looks something like this, and it may not be what you expected. We're going to come back to that we're going to come back to this in a minute, so hold on to that thought. We need to take a bit of a detour. Go ahead and pause the video. And we got kind of a triangle situation going here. See if you can figure out the pattern and continue the pattern. You think you got it figured out? Alright, so here's the pattern that I see happening here. You've got 1s going on along the edges, and then to find all the rest of the numbers, you add the 2 above it. For example, 1 plus 1 gives you 2. 1 plus 2 gives you 3. 3 plus 1 gives you 4. Or 3 plus 3 gives you 6. 3 plus 1 gives you 4, and so on. We could continue this pattern. For example, 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. This 4 plus 1 is 5. And we'll continue putting 1s on the outside. And we could just keep going. 1 plus 5 is 6, 15, 20, 15, 6. And again, just put 1s on the outside. This is a really cool sequence, a really cool pattern, and it's called Pascal's Triangle. You guys know Pascal from, what's it called, Tangled? He's named, I assume, after the French mathematician Pascal. This triangle has a bunch of really cool patterns in it. For example, and I'm about to nerd out here for a second. So if you look down each of these rows, I mean, this is all 1s, but if you look down the next row here, these are like counting numbers, 1, 2, 3, 4, 5, and so on. And then if you look at the next kind of slanted row, it actually is what we call the triangular numbers. You don't need to remember this, I just think it's cool. Like, the triangular numbers is the sequence of numbers. Basically, you can make a triangle out of that many number of dots. Like, you could make a triangle out of 3 dots, out of 6 dots, out of 10 dots, you gotta fill it in, and so on. And this row of Pascal's triangle happens to match that sequence. There's more. If you take the sum of each actual row of the triangle, it forms a sequence that should look very familiar to you. This is the sequence we talked about a lot in the exponential functions unit last year. Like, remember with the zombies we talked about, like you have 1 zombie and then they infect someone, so now you have 2 zombies, and they both infect someone, so now you have 4 zombies. This is literally the function 2 to the x. It's an exponential function. This one's kind of weird. Each line, if you just make them into like actual numbers, it's the powers of 11. Like, this row right here is 11 to the 0 power. This is 11 to the first power. This is 11 to the second power. This is 11 to the third power, and so on. I think that ends eventually because you get too high, but that's super cool. And this one's a little weird, but if you go like kind of diagonally and you add up these numbers here, you end up with the Fibonacci sequence, or the Fibonacci pattern. So like, if we do 1 plus 1, we get 2, and 2 plus 1 is 3. You add these up, you get 5. And this is a cool pattern, because the way this pattern works is if you take the 2 numbers before it and add it together, you get the next term in the sequence. So like 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. So those are connected. And if you take, in the second diagonal, if you take the square of a number, it's equal to the number below it and next to it. For example, if we do 4 squared, that's equal to 6 plus 10. 3 squared is equal to 3 plus 6. 2 squared is equal to 1 plus 3. There's just so many patterns, it's so cool. And maybe my favorite is if you just highlight all the odd numbers in the triangle, it forms the Sierpinski Triangle, which we talked about last year as well. It's a infinite fractal, one of my favorite geometric objects. So tons of cool connections. Pascal's Triangle is going to come back soon and help us actually solve stuff like this. It's going to help us expand this right here. It's also used in probability. It just has a lot of cool uses for just being like a random pattern triangle. So we'll get more into that later.